video. So so now, and I'm gonna put this up on YouTube. Although this one's probably better on the stream anyway, so you can probably access directly. Also, last time I think I said something, you don't have to write this one, but I think you had something like Q is equal to the activity of NADH plus times activity of proton divided by an activity of it's NAD plus and then NADH. Don't write this though, because I think you already have this. If you didn't have it, then you can just write it. And I think it's roughly the concentration of NAD plus times H plus over NADH. I think that's the way we left off last time. So this is again because it's a dilute concentration, so you can just use the concentration instead of activity. All right. Another example. So now we can start. So another example is so I'll just say another example. So because you guys did in analytical chemistry, right? So the example you had was the more like inorganic example. Let's say you have Cl2, right, and gas phase plus 2 electrons for the half reaction. And so this was a biological example, but Cl minus and then aqueous solution. So of course if you do reaction quotient, Q is equal to activity of Cl minus, right, product side, and the reactant side is activity of Cl2, right? And of course activity of Cl2, which is gas, so it's it's the actual, it's not solution. So in this case activity, right, is going to be equal to, in this case, going to be 1 anyways, or you can just call that in this case a gas phase. So it's not liquid, so we can't just use 1, turns out. So in this case activity of, in this case, the vapor pressure of Cl2. So keep that in mind. The reason why going from here to here is because activity of J is equal to vapor pressure of species J divided by P standard, right? So in this case P is equal to 1. So activity is a vapor pressure of chlorine, because remember Cl2 is a gas. So but ultimately again this vapor pressure, but it's again it's vapor pressure, so PCl2's numerical value, all right, numerical value is used. So keep that in mind. Is is the same as activity of Cl2. So keep that in mind. So all right, so you can just use activity of Cl2 as the vapor pressure. So keep that in mind. So when you don't know, you can just use the vapor pressure itself. All right, so now that's it. All right, moving on. So I'm going to erase that. All right, so again, that's just an inorganic example. But again, you only have seen it as a half reaction in the past. But now in reality, you can also do that for reaction quotient as well. So keep that in mind. Now that's it. I'm going to erase this, because now you can probably come back and watch the video anyways. And probably better resolution in bigger screen. So now, moving on. So now we are going on to the actual electrochemistry. All right, but electrochemistry, so electrochemical cells. All right, and again, easier place to start, and you have seen this before, is something like let's say you have 2 electrodes. So let's say let's connect 2 electrodes. So here I'm just going to draw 2 electrodes. And one happens to be zinc, the other one happens to be copper or something, let's say. All right, and then you put this thing into a beaker. And then of course if you make galvanic cell, you need something called salt bridge. All right, so I'm gonna just create a salt bridge, and these 2 electrodes are immersed. All right, so this right here in the middle is a salt bridge. I'm gonna just color that to black. All right. And then I'm just going to go like this. All right, it's a salt bridge, and you already know what the salt bridge is. It's just an electrolyte solution. All right, generally it has like sodium, and then anion. So in this case I have here inside we have zinc sulfate aqueous, and then copper sulfate aqueous. Of course sulfate solution in this case is actually you have so in reality you have copper 2 plus and sulfate, and zinc 2 plus and sulfate. So keep that in mind. These are aqueous, and of course here salt bridge is generally, sodium salt, sulfate is the same, but Na2SO4 aqueous is oftentimes used, so that the sodium doesn't play a role in the electrolysis or galvanic cell reaction. In this case, right, so you have copper and zinc. So when you look at the half reaction, zinc, right, going into zinc 2 plus 2 electron, and also copper, or in this case, well, let's see, let me think a little bit. I think I can just go ahead and make the reaction. So I'm going to actually erase this part right here just so that I can make a room. Just move this. You can just keep it there, but I'm just going to use a space here. So I'm just going to put zinc, right, going into zinc 2 plus 2 electrons, and then on this side I'm just going to go ahead the half reaction, but they are already balanced, and then redox, reduction, and oxidation are already coupled in this case, copper. All right. In reality, when you look at it, if you remember from maybe 260 or 270, you had a reduction potential table. By the way, reduction potential table will be given to you anyways. But 0.74 as a reduction potential, volt. In this case in oxidation, but reduction potential is in this case is 0.34 volts. So one side is reduced, one side is oxidized. All right. Net reaction in this case, 2 electrons and 2 electrons would cancel out. So in this case, copper 2 plus zinc going into zinc 2 plus copper solid. All right. And then electron cells total, so in this case E, all right, so in this case, so right here you just put E cell is equal to, I'm just going to use a space down here, but E cell is equal to plus 1.10 volt. The way I did it is because it's just this plus this is equal to 1.1. Pretty simple, straightforward. So keep that in mind. Remember, next to it right here, maybe you can probably write just so that you can make a note. You should probably use this space if you have one. I don't have one, so you can just write it here. I'm just gonna put just oxidized, and then this side you can just put reduced. All right. The reason why one is reduced and one is oxidized is because, remember, this, if you look at zinc, so you can just use a space right here. I'm going to use a space right here, but or you can just write it wherever. But anyways, if you look at the reduction potential table, zinc 2 plus 2 electron going into zinc. This is nothing you don't know. You already have covered this in previous analytical chemistry anyways. But remember, in this case, reduction, right? So zinc is picking up, zinc 2 plus is picking up electron. So zinc is actually, this part right here, this reaction is reduction. Reduction potential, if you look at the reduction potential table, it's minus 0.74 volts, right? So if you compare minus, the reduction potential of this value, all right, and this value, you don't have to write this part in your notes, but these arrows, you don't have to. But if you look at it, this side and this side, this value plus 0.34 plus 0.34 is higher, right? So higher the reduction potential in this case. So now that's where you want to take notes, right? So you can just go like, you can go like this, all right, and then like that, all right. The higher, right, the higher the reduction potential, right, higher the reduction, right, reduction potential, right. It's a potential, right? So higher the reduction potential, meaning more it wants to be reduced, right? Reduction potential is high, which means the species wants to be reduced, right? So that's why this side takes the priority. So this side is going to be reduced, and this side, on the other side, has to be oxidized, right? So reduction potential is low. That means it wants to be oxidized. So you're going to flip that, and then the reduction potential, the opposite sign will turn into that value. So in this case, minus 0.74 turns into plus 0.74. So keep that in mind. Now that's said, right? So, just that's how it goes. So when a coupled reaction, one side is reduced, the other side is oxidized. But in this case, what determines the oxidation reduction is the reduction potential, the likelihood of the species to be reduced. So keep that in mind. Now that said, just if you remember, just some terminology, which side is oxidized, I don't know, but you can look at it now. You can see this side is oxidized, but remember where the oxidation, all right, takes place, all right, we call this, terminology-wise, we call this anode. And of course, where the reduction, right, where reduction takes place, reduction occurs, right, we call it cathode. So keep that in mind. Just the terminology. So oftentimes, instead of saying like where the reduction takes place, we just call it, at cathode, this is happening. At anode, this is happening, and so on. All right. So, anyways, so that's good. All right. So just by the way, the reduction cathode, and how do you remember this? Oftentimes I'm pretty sure you heard this. I just call it red cat. Red cat, just a red cat, this is how Dr. DeBerry writes it, something like this, red cat, but then, it has to be red. But anyways, all right, so here we go. Red cat, reduction, all right, cathode, all right, so keep that in mind, all right. I should have brought the red pen, but that's okay. All right, so here we go. All right. So anyways, but of course, galvanic cell, it's nice to draw, but then it's pretty labor intensive, right, to draw the galvanic cell every time. So there's something called shorthand notation. So shorthand notation, and then shorthand notation is the following. So you have zinc electrode, and then it's a solid. And then there's a bar, and then zinc sulfate is the solution. So zinc sulfate, and it's an aqueous phase, all right. And then double bar, that means where the barrier is. In this case, barrier happens to be the it could be a membrane, could be it could be salt bridge, but the barrier. And then Cu, SO4, and then it's an aqueous. And then copper sulfate, right? And it's not sulfate, copper solid, all right? So let me explain what this means. Basically, this means sometimes you might see it as zinc 2+ aqueous, sometimes comma sulfate. Of course, well actually sulfate doesn't really play a role here, so you might just only see it as zinc 2+, all right? You might see it at zinc 2+, and this side you might see it's copper 2+. So you might actually see this, shorthand notation as zinc and zinc 2+, barrier, copper 2+, and copper. Again, you might have seen this in the previous chemistry, but let me actually write another example, all right? So you can continue down. I'm going to erase this because I'm going to run out of space. So let's do the shorthand notation again, all right? So let's say, what does, I'll just give you one more example. What does, this, all right, mean, all right? And I'm going to write this looking pretty complicated stuff. So platinum, right, solid, all right, bar, right, NADH, right, aqueous, right, comma, NAD plus aqueous, all right, and comma, H plus, all right, aqueous, and then barrier, right, H2O2 aqueous, comma, H plus aqueous. I'm going to run out of space. I'm going to continue down here, but bar, right, I'm going to just rewrite the bar here, all right, bar, all right, so I'm going to erase this one, all right, bar, O2, you can just keep it, and then you can just go and you can just make an arrow, all right, O2 gas, all right, and then platinum solid, all right. So, or you can just go like that and then go like that, all right. So now what does this mean, right? Well, it looks complicated, and it is, but remember, here's what I'd like you to do. We have to rewrite this again, all right, because otherwise it's gonna get too messy in your notes and you probably won't make sense. So we're gonna rewrite this, so write this fast. Aqueous, all right, and NAD plus, all right? I'm just gonna, won't say anything. You can just rewrite it. Just let's do it. Aqueous, right? Bar 2 gas, platinum, right? So now I'm gonna explain. All right. So now, so first, this platinum right here, and then you can also go like this. I'm just gonna go like here, right? These are electrodes, all right? Electrodes, right? Because they are solid, and it's also your textbook says one side should be cathode should be on the left, or the anode should be on the right, or vice versa, depending on which reference you look at. Personally, I don't care because it's really dictated by the. Personally, I don't care which way you write, but again, but you can do whatever the book mentions. General, it's dictated which direction the reaction occurs, which one's cathode, which one's anode, is dictated by reduction potential anyways. If you know that, you can do it. Sometimes you don't know. So anyways, in this part of the reaction right here, I'm just gonna go like this, or shouldn't have done this, but it's okay. I'm just gonna go like this. I'll just write it underneath. 2 electrons, all right, plus NAD, plus aqueous, all right, plus H plus, all right. Aqueous going into NADH. So in this solution, they're all 3 species are in this batch, and this is what's happening. All right. So, and then on this batch, you have a reaction that is taking place. I'm just gonna go like this again. It looks messy. That's why, I wanted you to draw it, because if you did up here, that gets really messy. All right. So H2O2. Is a result of reaction H plus aqueous, all right, plus O2 gas, and then plus 2 electrons. All right, so keep that in mind. Now, in this case, number of electrons already matched up, anyways, right? So, and then so what does this gas oxygen mean? It's right here. So what are these bars? All right, so here we go. So I call this this double bar, all right, as a barrier. Sometimes it's like a membrane, so it doesn't have to be a salt bridge. If everything is in one batch, then you don't even, if you don't have a barrier in the middle, like membrane or salt bridge, then you don't have this double bar. It can be everything is in one batch, and reaction will take place. If you put the whole thing in a bucket, all right, and then reaction still would take place, but then you won't have this double line. Now each, this white, this single line right here and single line right here, well, it gets really messy. It's just a, it's a phase, phase change, or phase. Well, you shouldn't call it phase. You should probably call it interface. All right, interface change. So in this case, it's in the aqueous, liquid, and then you have solid, so and then you have a solvent. So there's an interface change. It's not solid and solid. So in this case, solid, and then you have another solid, let's say. Then it's a 2 different interface. So you have 2 different things. You have a bar. So in this case, solid is in the solution, and there's a barrier. So when you see this, you should be able to imagine what kind of setup you have. So keep that in mind, right? All right, so I'm going to erase this, all right? It got a little bit messy because of the limited space, but I hope you have a clean drawing in your notes. All right, so let's switch a gear a little bit. All right, so now, we're going to come back to that, the shorthand notation, as we do some examples later. But let's say, we've been talking about delta G, so, let's talk about, how does delta G, right, relate to the reduction potential, or or in this case, not reduction potential itself. It's just the electromotive force, EMF, or you guys call it, the voltage, the cell voltage. All right. So from physics, by the way, if you remember, work, known expansion work that you saw in the previous chapter, non-expansion work, right? Expansion work, expansion work was like, PDV, right? This is expansion work, right? So, or you can call it PV work. PV work is the PDV, right? But also, non-expansion work, that doesn't actually do the actual expansion part, is the delta G, the Gibbs energy, right? So, assumption this was, at, constant temperature and constant pressure. That was the assumption we decided, all right? But also, also the non-expansion work in terms of cell voltage is also non-expansion, right? Non-expansion work. Of course, in this case, electrical, right? Potential. In this case, reduction potential is the electromotive force, right? Is the cell voltage or cell potential is also minus NFE, right? That's from physics, and you probably remember this as dW is equal to minus NFDE or something, right? But anyways, if you took calculus-based physics, but anyways, in this case, so this is equal to this, and also this is equal to that as well. Where also, I'm just going to put also, right? So then, right? So that means it's like A is equal to B, B is equal to C, so A is equal to C, right? So it's like delta G, so hence, right? Hence, right? Delta G is equal. Oh, by the way, NFE, I mean, just so that you know, it's Faraday's, I think Faraday's constant. I think we talked about this, and E is just E is the electromotive force, EMF, and then N is the charge number. I'm just going to use the up space right here. The electron number, number of electrons being in the reaction. So which means, by the way, number of electrons, all right, number of electrons is like, let's say if you have something like let's say if you have like A plus like N E minus going into like B or something, right? So in this case, if it's 2 electrons being involved for like a copper, then that's going to be 2, so keep that in mind. But anyways, delta G is equal to this, so delta G is equal to minus NFE, right? Well, so again, kind of cool because delta G is related to the the EMF as well, all right? So keep that in mind. So of course, delta G is now, of course, delta G, of the reaction, was, delta G of the standard condition from the, and then plus the deviation from it, natural log of Q, right? So, of course, if this term is equal to 0, then this is equal to that. But, again, delta G of the reaction is dictated by how much reactant and how much product you have, right? Because it deviates from the standard delta G, right? So, but reaction quotient, wait, earlier we kind of did the reaction quotient with the activity, right? And then also for the half cell reaction, right? So, this, this, is going somewhere. It looks interesting. Well, man. Anyways, like going back. So, wait, delta G is equal to that too. All right. So, where is it going? All right. So, remember, delta G of the reaction, or delta G of the reaction, all right, is equal to minus NFE, is what we did, what we said earlier, right? So we can convert this, so then we can convert this, all right? This to, we can just solve for E is equal to minus delta G of the reaction over NF. Looking good, all right? And I think I'm running out of space on the camera, so I'm going to go ahead and erase that. All right. So then, so also, let me rewrite this. E is equal to minus delta G of the reaction over, NF. Of course, if you have, and you can just write and. Of course, if it's a standard, delta G, then it's going to be standard cell potential. So, I'm just going to put E0 or E naught is equal to delta G naught over NF, and of course we need the minus of that, right? So wait, this and that relates to delta G. Wait, so if that's the case, we can just rewrite this. The whole thing is like E is equal to E0. Of course, you had E divided, well, NFE, right? But then you can put the NF on the other term. So I'm just going to simplify it all together. Minus RT, natural log, well, natural log of Q, but then divided by, NF. So originally, remember, it's, NFE, right? NFE is equal to minus delta G, right, of the reaction, right? So minus sign was here earlier, but then take the NF to the other side, right? Right. So then you just have E, and then you just combine it over here instead, right? I just algebraically just worked out, all right? So now this is kind of cool. It doesn't look, that doesn't look cool. Let me rewrite this because it looks really cool. So here, natural log of Q. What does this mean? This means, right? This is again similar to what you saw earlier with delta G is equal to delta G standard minus RT, right? Natural log of Q, right? But so this is the actual potential that you can get, right? Right, when you have a mixture of product and reactant, or if you have a starting material, right? So you have a cell, standard potential, but then deviation from it based on the product or based on the reactant you have, how amount you have, that would change the actual output, right? So in this case, you can call it actual, right? Actual potential, right? Actual potential, right? At non-equilibrium condition. This is kind of cool because now, again, you know that if you have copper and zinc, you would get minus 1.1 volt, at the standard condition, which means, again, you only have a certain concentration. In this case, this part doesn't play a role, right? But let's say you have lots and lots of, one of the concentrations, right? Then that would affect the Q. So overall output is not going to be 1.1. It could be more, could be less, depending on how much product or how much reactant you start out with. So keep that in mind. It's kind of cool, right? So of course, at equilibrium, right? And also equilibrium. Of course, at equilibrium, Q is equal to K, right? And at equilibrium, potential is equal to B, is equal to 0. So keep that in mind, right? So because remember, because equilibrium, right? At equilibrium, system, can't. I'm just gonna put because, right? At equilibrium, system can't do work, right? So keep that in mind. So in this case, it's 0 is equal to E0 minus, RT over NF, all right? Natural log of K, all right? Well, kind of cool. Then, what does this mean? Well, wait, so this is 0, so you can take this, all right? This E standard to the other side of the equal sign, and you have minus sign of that, so you can call that, E0 is equal to E0 is equal to RT over NF natural log of K. Wait, delta G is related to, delta G is related to E. E is also related to E0, right, when non-equilibrium condition, but also when equilibrium, Q is equal to K. So so that means the standard cell potential is related. Standard cell potential is related to the equilibrium constant. Man, it's like all related. How cool is that, all right? So underneath here, I'm just going to erase this space right here so that I can make a room, but you can write it underneath here, all right? So here, let me write this down. Here, it's equilibrium, right? Equilibrium constant, right? And, standard potential, right? Potential, right, are now related. How cool is that, right? So everything is related. Man, it's like all related, right? Kind of cool, right? So, right. So now, so of course, in biological condition, roughly, pH, our case, pH, we don't have pH is equal to 1, right? Like standard condition. So it's like, 1 molar. So, we have to think in terms of like, pH 7. So we have to, use something called biological standard condition, right? So converting, standard, which is, typically it's 1 molar, but standard E, naught, right, to, what we call biological standard. In this case, at pH is equal to 7. So, right, so, if you look at, just an example of NAD plus, aqueous, all right, plus H plus, aqueous, plus 2 electrons would go into NADH, right? And then that's NADH, and then E. So in this case, E 0 is equal to, minus 0, I'm going to use this space here, 0.11 volts, right? So anyways, but, so let's say, E is equal to E standard, right, minus RT over NF. Oh, sorry, it's in this case NF, but we already know it's 2, so I'm just going to put 2 here. 2 electrons, all right? So 2 electrons, so 2F, all right, times natural log of Q, right? But then let's think about this Q a little bit. So in this E0 is, going to be 1.1, but we're going to come back to that, minus RT over 2F, all right? Natural log of, then activity-wise, we have activity of, NADH and activity of H plus times activity of NAD plus. But when you look at the half reaction, whatever the number it's converted, right, it's going to be the same, right? This and this is it's a one-to-one stoichiometry. So if this gets converted into that, right? So whatever the number, so in this case, these numbers would cancel out, right? So in this case, it's going to be is equal to, because it's a half reaction, so keep that in mind, only applies to half reaction. But E standard, right, minus RT over 2F, natural log of, in this case, natural log of 1 over a proton, right? Of course, it's minus, but then it's 1 over that, so we can just, I don't like negative sign in the equation. I try to make it positive, RT over 2F, and then, natural log of activity of, H plus, right? This looks messy, so I'm just going to rewrite it, H plus, right? So 1 over that, so minus to the first will make it positive, right? Then, so what does it mean? So now, well, it's simply then, so how much, so what happens in this case, all right? Well, it's H plus activity, a pH 7, at, in this case, dilute solution, it's going to be what? It's like 10 to the minus what? 7th or something, right? A natural log of, so, and then you have, so natural log of like 10 to the minus 7th, right? And then you have RT and 2F. So if you do that, turns out you can just plug and check. I'll just give you the number is equal to minus 0.11, right, volts, right? Minus, I'll just give you the end result, 0.21 volts, right? And then is equal to minus 0.32 volts, right? So again, this is based on, 10 to the minus 7th, all right? So keep that in mind. And then you can just plug that in. All of these are constant at, 37 degrees, right? So in this case, 37 degrees, and what is it? Or could be 25. But anyways, I don't remember how I did this. But anyways, it's a 25 or 37. But either way, it's 10 to the minus 7th, right? And then these are constants, and then R is constant. So at the end, you get minus 0.32 volts. Kind of cool, right? Sorry about that. This is not E0. E0 turns out, or E0 is that. Sorry about that. This sign, I should rewrite this. All right, let's just go like this. Let's rewrite this. Biological standard condition is actually not. It's actually I think the book uses this, plus sign somewhat. I think that's how it's written, right? So again, it denotes the standard condition. Typically, standard condition, I write it this way, but this is the biological. So biological standard condition. So keep that in mind. All right. Anyways, so all right, kind of cool. So now, what else? So of course, so now the the delta G and and E is related, right? So and then remember, delta G is a what we was the state function, right? State state function, right? Which means it's a path independent, right? So which means E is probably going to be the state function as well. So keep that in mind. So state function means we could use Hess's law, right? Right? So which means we can also do that with, we can do this as well. We can do this as well. There's one minor difference that you have to be careful, right? But I'm just gonna go like this, right? With minor mods, modifications, right? So keep them. You probably don't want to use. I say mods, but modifications. But you probably write it down as like a modification, right? Instead, because otherwise you go like, what's mods? Anyway, so here we go. So calculating, right? Calculating, because sometimes you don't know how the cell potential is being, what the cell potential is for that particular reaction. Sometimes you don't know. So just like Hess's law, sometimes you don't know the actual Gibbs energy or enthalpy, but you can actually use Hess's law to go around and you actually calculate that particular the thermodynamic parameter. Remember, the cell potential or EMF in this case is also a thermodynamic parameter. So you can actually determine that by using the very similar method with minor difference. But calculating, standard potential, right? Potential from two other potentials, right? So let's say I'm gonna start with ABC, but then I'm gonna start with C first. All right. So I'm gonna just do C and then AB, but start with C. All right. Or 2 minus, all right, aqueous, all right, plus 2H plus, right, aqueous, right, plus electron going into H2O2, and then E standard, right? What is it, right? So and then two other value. I'm just gonna put A and B. A is O2 gas plus electron going into O2 minus aqueous, right? The E standard is equal to minus 0.45 volts, right? And then O2 gas plus 2H plus aqueous plus 2 electrons going into H2O2. And then aqueous. Now you see where it's going. E standard, right? E standard is equal to plus 0.30 volts. All right. Okay, simple. I mean, so when you look at it, you can immediately see that. Wait a minute. It's like if you flip one of the reactions, all right, and then change the E potential. You can technically speaking, or cancel out and look something like that. What if you flip one of them that would resemble, right, something like this, anyways, right? So it's like it has Hess's law, except there's one thing that you have to be careful. So underneath here, let's write it down. We're gonna come back to this, this note for A and B, right? I'm gonna call delta G first. This is what you have to do, all right? We can't just flip it and then just add these up. Remember, G, the Gibbs energy, it's an energy. So energy you can add, but E is a potential, all right? So potential you cannot add because it relates to an energy, but it's not an energy, all right? So remember, this is not just simple. Again, it's something to do with intensive extensive property. In this case, right? In this case, you can't just simply add. I'll come back to that in a minute. So this is what's going to happen. Delta G of the reaction. I'm just going to put, one side, delta G of the reaction, all right? I'm going to call this of a delta G of the reaction of A is equal to minus F NFE, right? So in this case, 1 times F times E is equal to minus 0.45 volts, right? NFE, right? So in this case, minus and minus, so I'm going to call it plus 0.45. I'm just going to use, you can just put volts times the Faraday's constant. I'm just going to put Faraday's constant. They're going to cancel out at the end, so I'm going to just keep it, out this way. Delta G of the reaction for reaction B is equal to, in this case, minus 2F times, 0.30 volts, right, is equal to, I'm going to just go ahead and calculate this, so it's a minus sign, so it's going to be, is equal to minus 0.60 volts times, F, right? So, now finally, again, in terms of reaction, again, it's Hess's law. So again, these steps are, you can apply Hess's law. So you can actually do C is equal to, in this case, you flip one side, so you can just call it B minus A. So I'm just going to do, so delta G of the C, all right, is equal to, or reaction of the C is equal to, delta G of the reaction of, B minus delta G of the reaction of A, right? That's what Hess's law is, right? So is equal to, in this case, but remember, in this case, each one came from here, right? So you have to plug that in. So in this case, minus 0. B is this, all right? So 0.60 volts, right? And then for, F minus, all right? And the minus 0.45 volts, all right? F, right? I'm going to use a space up here going back, all right? And I'm going to use a space up here, all right? So this minus this, okay, that's fine. So, and then this is equal to, I'm going to just use the space right here. You can just continue down, right? This part right here can go up to here. Just use this space down underneath, but is equal to, remember, you can, well, it's that, but, is equal to, is NFE, right? Remember, this came from here, right? Delta G is equal to this, right? But is delta G is equal to NFE, right? And this is a standard, right? Right, so keep that in mind. So in this case, all right, so is equal, so the left hand side of this part of the equation, it's going to be something like what? This minus that, so it's minus, right, 1.05 volts, right? Volts, all right, times, F, right? Times F, right? Times F, all right, is equal to, NFE. But, in this case, N is equal to what? It's equal to 1 already. So, turns out this is equal to 1 because you already, in this case, what's left of it is 1 electron, right? So, 1 electron. So is equal to Fe, standard. But then F and F also cancels out. So E0 is equal to, minus 1.05 volts. So remember, you can't just add the value. So because if you remember this, this part right here, E0 is equal to, what was it? It's minus 0.45 volts, right? So if you just flip one, right? If you just flip one, right, and then try to add, they are not going to be this, right? Because remember, the reaction itself is, you can apply Hess's law. But, Hess's law only applies if you are dealing with the energy. Because you're dealing with energy. You're not just potential. You can't just add potential. So keep that in mind. So that's the major difference. I mean, it's minor difference, but it's major enough that a lot of people actually make a mistake on this, right? So you can't just add potential, right? Because potential needs to be converted to energy first. because energy you can add, right? So keep that in mind. So that's why, you know, there are multiple steps here, but what you're really doing is just setting it up. And you have to account for the number of electrons, and that's the difference, all right? And that's a common mistake, and that's the major, most frequently found mistakes in standardized exams. So I just wanted to tell you that, right? So keep that in mind, right? So now that's it, all right? So kind of cool. So it's not a simple just adding the potentials. You actually have to account for the number of electrons, right? Anyways, all right. So all right, so let's see what else. So now, so you know, we did the just a review. So free energy, right? The Gibbs energy, all right? Gibbs energy, right? You know, is related to equilibrium constant. Equilibrium constant, kind of cool, right? And then, you know, free energy also is dictated by the, you know, what others, you know, what species are in the reaction. So it's related to, you know, reaction quotient, right? Reaction, right? Quotient, right? Right? And then these are related, but equilibrium constant and reaction quotient is also related to, you know, electromotive force or electrochemical potential. Electrochemical potential, or an electromotive force, and you can call that EMF for short, right? So they're all related. It's kind of cool, right? So now, but, you know, of course, you know, when I mentioned that it's all related, and then, you know, of course, someone will go like, prove it. So here we go. Prove it. So delta G is, so dG is equal to minus SDT, all right, plus VdP, all right? You've done this derivation in the previous chapter, right? Of course, you know, SDT come from the, you know, actual the Q part, all right? You know, remember, you know, you had this G is equal to H minus Ts, and you went through all these steps, and eventually you got here, right? So now from here, you know, at constant, right, constant pressure, let's just make the life a little bit easy, all right? Constant pressure, dP is equal to 0, right? So then dG is equal to minus SDT, and then, well, dP is going to be 0, you know, then, you know, dP is equal to 0, right? So, and SDT, all right? So if that's the case, then, you know, you have dG and dt. So, but if you, let's say if you change, well, so if you do, let's say, I'll just do a, you know, well, let me think a little bit. If you actually, you know, SDT, S right now is a constant, but let's say if the entropy changes, then G changes, right? If S changes, G changes, right? So, so I'm gonna make this, you know, say, let's say is equal to, let's say, so I'm just gonna, well, you don't know how to do this, but it's okay. I'll just give you, I'll just give you the end result. If you change, and if the entropy changes, all right, so dt, and then the whole thing, I mean, if you look at it mathematically, it will make sense. I mean, it's, you know, delta G, I mean, but G changes accordingly, right? So if you, you know, and then because it's a minus sign, this turns into, you know, because it's, you know, the G of the final minus works out as like this case, right? So anyway, so it's so I'll just give you the end result, right? So dG is equal to minus SDT, but if you change, you know, delta S, if you change the delta S, that would change the delta G, but then that's, you're still taking the D, so keep that in mind. But anyways, so delta G is equal to, you know, delta G is equal to, you know, so remember delta G was, you know, is, you know, minus NFE is what we have been, you know, dealing with, right? So standard is equal to NFE of the, you know, standard, right? So you can call this, you can put this thing inside here, so it's like D of the, you know, D of the minus NFE is equal to, you know, delta S, you know, dt, right? Of course, you know, you have D of that, and E, you know, is the cell potential, or, you know, it's a, you know, potential, you know, it's a, you know, it's a voltage, right? So it's, so in this case you can take dE. So underneath here, I'm going to use a space up here, all right? So you can call that as, again, it's minus sign here, but you can call this as a, NFE. All right, I'm just give you the end results. NFDE, all right, is equal to delta S, all right, delta S dt, all right. So what does it mean? So, and if you solve for, solving for delta S, all right, will give you, delta S is equal to, NF, dE standard over dt. Just take my word for it. It's okay. You only had Calc 1, so it's perfectly okay. Okay, no problem. All right. So just take my word for it. Just the transformation in this case just goes from here to here to here may not sound intuitive. All right, but but D just the number of the species don't change. Faraday's constant, you can't really take D, so only thing you can change is the E anyways, and then just minus sign just turns into positive. But anyways, so what does this equation mean? Well, so here we go. Here's the cool part, right? So the cool part is that if you have temperature, right, and then you have temperature, and then of course you have standard cell potential. Of course cell potential changes, right? Standard EMF changes if you change temperature. I mean, if you think of battery, for example, and just simple alkaline battery or something, right? And if you measure the voltage at like room temperature, like 1.5 volts when it's new, it's more like 1.5, 9 or something. It's almost 1.6 volts when it's new. But if you put that alkaline battery into the fridge or something, and after you take it out and you measure the voltage, it's lower than 1.6. It's gonna be like 1.5, 1.49, right? So E versus T has a certain curve. So keep that in mind, right? Of course, if you take a derivative, right, dE over dt. So if you take a derivative of that, all right. So if you take a derivative of that, that's a dE 0 over dt. So keep that in mind. So guess what, right? This, all right, this will give you the delta S, because N is going to be constant, because that's the electron number you're dealing with. F is a constant, right? So this is actually related to, it's proportional to delta S, entropy, all right? So again, if you actually can measure the E, so here's the cool part, right? If you actually measure the E, right, and if you change temperature, and then they respond accordingly, right? The voltage responds to the temperature accordingly, right? So if you actually measure the the voltage, based on the temperature in response, and it relates to the entropy. So in fact, you can actually calculate the entropy of that particular reaction. So here, so experimentally, so here's the important part. Experimentally, right? E0, right, can be measured, right? With respect to, and this WRT, with respect to temperature, right? Then delta S, right, can be determined for that reaction. Determined, right? So again, of course, and experimentally speaking, if you only do like 2 point, oftentimes if you do every single point, that would be great. But oftentimes the people just do 2 point determination. So oftentimes delta S of the reaction is equal to NF, and then E, E standard minus E standard at the alternate temperature. I'm just going to put dash, all right, over T is equal to dt. So it's a T minus T dash. Right. So again, T and T dash and E dash is the those numbers according to that particular temperature. Right. Kind of cool, because then you can calculate the entropy of the reaction. Of course, by the way, this is the I laugh because this is the reaction that you didn't get to do in the lab. All right, it would have been really cool, but again, this is already toward the end of the semester, and even if you did the experiment, chances are you might not have had actually chance to actually write it up anyway. So, every year, I fail to do this experiment because we run out of time. But anyways, but it's kind of cool though. You can actually measure the entropy because you know from calorimetry you can actually calculate the delta H from the combustion. You didn't do that, but Anyway, so remember delta H, all right? Can be also can be found, all right? From E0, because if you know the delta G, if you know this value, you can get delta G, and you also can get this by varying temperature, and then you can get that because delta E and delta S, right? So remember, right? So this relates to again relates to delta G, and then this is relates to to E0 and temperature, right? And then because G is equal to H minus Ts, right? So keep that in mind. Kind of cool, right? And that concludes this chapter. Done! Yay! All right, so that's the end of this chapter. All right, so let's take a break. All right, I'm going to talk a little bit about the problem set. So let's take a 5 minutes break or so that you can stretch, and you guys can get food or drink or something, and then we'll just reconvene at 2:06, 2:07, something like that. Right? I'm going to erase the board, and I'll see you in about 5 minutes. All right, I'm going to stop the recording now.